So up to now we looked at one type of stabilized method in the residual-based stabilization context. And honestly, I would say we've looked at one stabilized method because I don't even want to consider artificial diffusion as a stabilized method. It doesn't fit our criteria for a good method. It's not very easily consistent, so we only consider that to be a stepping stone to a good method, and that was SUPG. Now in this video I want to emphasize that that is really just one of the residual-based stabilized methods that exist. And all of them kind of take the form that you're seeing right here, where we have our standard bilinear form all the way on the left, and we have our standard linear form all the way on the right, and now we're adding this residual-based term in the center. And in the previous video we emphasized that we actually would have to write this as the sum of element contributions, where we have per element the residual being weighted by tau times tau being a stabilization parameter times some differential operator acting on W. So this is a general form of writing these methods. And again, R is the residual of our finite element solution. In the strong form, so if we write our partial differential equation as differential operator acting on phi is equal to F, then the residual is going to be, the residual of phi is going to be equal to F minus L of phi. Now, I hope that you realize here, and that's something that when I started looking into these things, I was not completely aware of, or I didn't realize until a little while after. The residual is not the same thing as the error, right? Remember, the error is the difference between the solution and the finite element approximation. So that's something else than the residual. The residual is the difference between the true differential operator, so and the differential operator acting on our approximation. And we can actually see that if we define this to be equal to E, the error, then the residual is actually equal to our differential operator acting on the error, because our differential operator acting on the error is, well, assuming we use linear differential operators, is equal to that, right? That's just substitution. And this is going to be equal to F by definition of it being the true solution. Yeah, so the residual is actually not directly the error, but it's the differential operator acting on the error. So it's a different way of interpreting the error. And just like the error is going to be 0 when we have the true solution, also the residual is 0 if we have the true solution. Okay, so that's one of our components in our residual-based stabilization methods. Then another very important component is tau, that's the stabilization parameter. Something that I actually haven't talked about yet, and I'll also not talk about in the first couple of videos still. Only once we've built a little bit stronger foundation do we start to talk about these parameters, because there's different ways that we might obtain these parameters. There's also different constraints that we have when we consider this parameter. They're not allowed to be too large, they're not allowed to be too small, and we might want to delve a little bit into the physics to decide what this parameter might be. So that's another component, and then clearly the last component is this else tab. Let's see, what did I call that before? You can refer to this as the stabilization operator. And choice of this else stab really gives different stabilized methods. Yeah? The change in the parameter, the stabilization parameter, will also give you a different solutions and different formulations in that sense. But we call those the same method, right? If you choose a different parameter, but you still use the complete same SUPG formulation, then we still call that the SUPG method. Yeah? So the different methods, they kind of reside in the different choices of the stabilization operator. So let's start with what we know. We know SUPG falls in this example class, or in this classification, where for SUPG we're taking the choice of L stab is equal to A dot gradient of WH. Right, if we have A dot gradient of W, or maybe, sorry, I should not have H here. A dot gradient, because if I plug in A dot gradient here and I act it on W, then you get A dot the gradient of W, and that's precisely what we had as our SUPG formulation. Now, why did we do this again, coming from our original line of argumentation? Well, really the only reason why we are left with this A dot gradient on W is because we started off coming from a interpretation of artificial diffusion, and then we made this a streamlined diffusion, and then we saw that leads to this A dot gradient. But that's honestly the only reason, and there might be more terms in this stabilization operator. And indeed, for other stabilized methods, we have more extensive stabilization operators. So another example is going to be variational multiscale. Sorry, I should be a little bit more careful. If I have a plus here and I define the residual like this, then my L stab has to be minus that. Variational multiscale, VMS stabilization. There we choose L stab to be equal to the adjoint differential operator. So that's the original differential operator L. That's what this refers to. And the star means the adjoint. So this is the adjoint differential operator. Now, what's the adjoint differential operator? That's the operator that you would obtain if you would perform all the integration by part steps. So if I take the original differential operator to be A dot gradient minus kappa Laplace operator. Then if I do integration by parts twice, if I do integration by parts once, I would change this to, this will become, depends on how much detail I want to explain this. You know what, I'll go into full detail. So the adjoint differential operator is the operator such that this is true. For all w's in, actually now we have a new space that I haven't really talked about, is the space of test functions. So what's special about the space of test functions? Space of test functions are sufficiently differentiable such that we're allowed to do these operations, and all their derivatives vanish on the boundary. And that means that integration by parts doesn't give us any boundary terms. So if I then have A dot gradient minus kappa times Laplace operator here on the left, and I do integration by parts, then I would obtain phi comma A dot gradient on W. And normally you would get a boundary term, but again, because the space of test functions, all boundary values and boundary derivatives are 0, that doesn't show here. And after one integration with parts, I would get kappa gradient phi gradient w. Now I perform, oh sorry, there should be a minus here, right? Because every time we do integration with parts, we have a flip of the minus sign. So now we do one more integration with parts, and then we get minus phi a dot gradient w minus phi kappa Laplace operator on w. Right, so what we're actually seeing is that the adjoint operator for the diffusive term doesn't change. It's still minus kappa times the Laplace operator. But for the advective term, it actually changes its sign. It's because it's an odd order operator. So long story short, for the advection diffusion equation, L star is going to be equal to minus a dot gradient minus kappa times Laplace operator. Right, so if we compare that to SUPG, then we find that we have the same leading term, but we have one more term. And now you might ask, why do we now get one more term? Well, there's actually a pretty strong argumentation underlining variational multiscale, and that's something that we'll get back to once we start talking about multiscale modeling for fluids, because this is actually something that follows from the lines of thought that we'll introduce there. So then we have SUPG, we have VMS, and as a last one that I want to point out, we have Galerkin / least squares. Galerkin least squares. And there we're choosing the differential or the stabilization operator to be equal to the differential operator, or minus, equal to minus the differential operator. So again, what does that look like? In the case for the advection diffusion operator, you would again get minus a dot gradient times the function, or acting on the function, plus kappa times that second operator. Okay, so that looks a bit like VMS, but we flipped the sign here. Now, why would we want to do that? And actually, that's the first thing that we're going to talk about after this video. I'll focus on the Galerkin least squares method, and actually I'll start with just exclusively addressing the least squares formulation, because that's a whole different. The Galerkin formulation is one way of obtaining finite element formulations. A least squares method is a whole different way of obtaining finite element formulations. Now, there's certain problems with why least squares formulations don't always work, or are very difficult to implement, and that's why we're combining this with the Galerkin method. So this is a Galerkin method in combination with a least squares method, and then you can actually show that that's exactly something that takes on this standard form that we have here, with as a choice of stabilization operator this operator right here. So it's a little bit of an overview of different residual-based methods, some of which we'll go into depth already pretty soon, and others we'll talk about later. The one thing that I think is very important, and that's pretty much the whole reason for why I'm making this video, is just the general classification here. The classification of residual-based stabilization in this sense, that we have our original Galerkin method, and we add now this element-wise residual-based weighting with a stabilization operator acting on the test function. This is something that doesn't exclusively have value for fluid mechanics. This is something that might also have value for solid mechanics. One example is the case where you where your material constitutive law is starting to tend towards incompressibility, that you have an incompressible material, and often rubbers are considered incompressible. You would obtain unstable finite element formulations in that limiting case. So also for those cases, you can get instabilities, and this applies as a stabilized method then. Right? So this is really not something that is only important for fluid mechanics. And also in fluid mechanics, let me also be clear, this is not something that exclusively has value for the advection diffusion equation that we've chosen as our model equation, right? So the same formulation applies if you want to stabilize the full Navier-Stokes equation. Now then you have to think a little bit better about what the residual is going to be, because we're talking about a mixed formulation and a vector valued solution field rather than scalar valued. So we have to extend it a little bit, but the basic principle is the same. Yeah? And I think this is so important that I can tell you right now that this is something that I will ask a question about during the oral examination. I want everybody to be familiar with the term residual-based stabilization. So if I ask you a question in the direction of what is so special about SUPG, GLS, right, Galerkin least squares, GLS, or VMS as stabilization methods, then I want you to say, well, the residual based. That's the thing that I'll be after when I ask a question like that. Okay, so that's something that you should not forget and not underestimate. Okay, thank you for your attention.